Hi everyone, welcome back. Today, as promised, we're going to go through a review of at what at Oregon State is Math 256, okay, where you learn how to solve ordinary differential equations. For a lot of people, this class, and there's other classes that you may have taken with this content, especially if you came from another university. You know, in this class, more broadly speaking, you are responsible for being proficient in dealing with ordinary differential equations of various types in an analytical way, in addition to being able to solve them numerically, which is what we actually learn. That's sort of the new content. But you need to be able to solve them analytically to perform that verification and validation that we mentioned last lecture, where you want to make sure that your implementation is correct of a certain solution method, right? So you want to look at the analytical solution versus a numerical solution of an equation, which is the exercise that we did at the end of the last lecture. But since these courses, like Math 256, may have been a while ago, we're going to run through these topics once before proceeding. So this lecture is going to be a little bit dry. If you're feel very strong in these topics, you can probably just skip it. But I would encourage you to go through it one more time just to remind yourself about all these things. But let's take it all the way back to the general first order linear ODE. Okay, and once again, we'll talk about what all these terms mean in detail. Right. Okay, I think we might do that at the beginning of lecture 3. Let's see. Yes. Yes, so we'll do that at the beginning of the next lecture, just to review what those terms mean. But for now, let's just talk about the solution methods. Okay, so the most general form of this equation, I shouldn't be using partial derivatives here, is the following, where you have dy dt plus some function p of t times y is equal to another function g of t, where y itself is some unknown function of t. Okay, imagine the functions p and g are actually just constants. Then you have the form of the equation that's the form that you would always hope for when encountering an ODE. It's separable. Then the equation is separable. And you can just move the dependent and independent variables to either side and integrate. So in this case, you would have dy dt is equal to g minus p times y. Okay. And to solve this, we go 1 over g minus p times y. dy is equal to the integral of dt. And what that translates to when we do u substitution, so you say u is equal to g minus p times y, du is equal to minus p dy. That will give us minus 1 over p times the natural log of g minus py. The natural log of the absolute value of g minus py, which is equal to t plus some integration constant c. And then we do a little bit of algebra, exponentiate both sides. We have g minus py is equal to c1 e to the minus pt, where c1 is going to be basically e raised to the power minus pc. Okay, it's just another integration constant. We're just wrapping things up in constants here. And then the final solution for y is c2 e to the minus pt plus g over p. Okay, so that becomes our solution in that case. Okay, now, more generally, for separation of variables, which is what this method is called, and I'll highlight it really quickly just to make it clear that this is a solution method, where your derivative dy dt is some function of t and y. You just need to be able to rearrange to the following form. Need to rearrange to the following form, where you have some function m of t plus some function n of y times dy dt is equal to 0. Okay, and then you will find your solution by integrating m of t dt and setting that equal to negative n of y dy. Okay, and now that if you perform those integrals and solve for y, you'll end up with your solution. In this case, n of y is 1 over g minus py, and m of t in this case is just 1. And then the example that we just did, rather. Okay, so that's our sort of most simple solution method, just the method of separation of variables. It's actually very common that you'll encounter equations that are separable, even for physical systems, especially simple physical systems. So you'll want to keep that one in mind. The next method that we'll talk about for solving ODEs is the method of integrating factors. And this method was actually developed by, it was developed by Leonhard Euler in 1740, right? And I like to tell students who came up with the methods, or when something is named after somebody, I like to go over a little bit of the history of that person. And Euler is, in my opinion, I think it's pretty cut and dry that he's the greatest mathematician who's ever lived. Here's an image of him. And when I was first preparing this lecture, I was like, okay, let's give the students an idea of the scope of his work. Euler, during his life, he published I think like 500 papers in books, and then there's another 400 or so that were published after his death. I think the estimation is that during his working life, he did about 800 pages of work per year, which is just completely astonishing and ridiculous. But as a testament to that, there's actually a Wikipedia page for a list of topics named after Leonhard Euler. And and I'm going to zoom out here because I put all of them into this thing. You can see the list just continues on and on and on. Formulas, identities, numbers, theorems, music, number theory, polynomials. It really just doesn't end. And I find this passage from the Wikipedia article really funny, where it says that his work touched upon so many fields that he is often the earliest written reference on a given matter. In an effort to avoid naming everything after Euler, some discoveries and theorems are attributed to the first person to prove them after Euler. So you really can't touch this man in terms of impact on mathematics. And another fun fact about Euler is he and his wife actually had 13 children, only 5 of which made it through childhood. But he spent a lot of his years, surrounded by children. He did a lot of this work with a bunch of young children around him, and I think he's quoted as saying that he's never more happy than with a baby on his lap working on a mathematical problem. Which, as a dad myself, I find that really inspiring. That the greatest mathematician of all time was also a great dad, and certainly for the time a very involved dad. He spent a lot of time with his children. So That's a very, very interesting person. I mean, he literally solved, I think he worked out the orbit of the moon after he had gone blind in his head. So he was barely human, but but due to his work, we can solve differential equations and do all sorts of different things in mathematics using the discoveries that he made. But today, the first thing that we're going to learn that Euler developed was the method of integrating factors. Let's make sure we get the everything right here. So let's consider the following equation, where we have dy dt plus p of t times y equal to q of t. So a first order linear differential equation. And it's non-homogeneous as well. So linear first order. So linear has to do with the fact that there's no functions of the dependent variable or its derivatives that are nonlinear. And then first order has to do with the highest order derivative that appears is the first derivative. And then it's an ODE because there's only one independent variable. And then it's also non-homogeneous because there are terms in the equation that do not contain the dependent variable. Okay? So the basic idea of the integrating factor is the following thing. So basic idea, we want to rewrite the equation in the form d by dt of mu of t times y is equal to mu of t times times q of t. Okay, and then we can then just solve for y by integrating the right-hand side and then dividing by mu of t, right? So if we can get the equation into that form, then the solution becomes straightforward. And again, we're using primed coordinates here just as a dummy integration variable. Comes mu of 0, y of 0. Okay? So you can get that solution. So to find mu, we basically want to just match both sides of the equation. So to find mu, match both sides. So what do I mean by that? Well, first let's evaluate that d by dt of mu of t y. That's using the chain rule, or sorry, the product rule, d mu dt times y plus mu dy dt. Okay, so remember that. And then we multiply both sides of the original equation by mu of t. Mults OG equation by mu of t. That gives us mu of t times dy dt plus mu of t p of ty is equal to mu of t q of t. So we can see here that we've got this matches, right? And then we evaluated what the thing on the left is. So now we can just we can compare the two things that I'm going to underline in blue here. These should be equal to each other, right? If we're trying to build this overall structure here, that allows us to get that simple, or not simple, but defined solution. So if we compare those two, those two things underlined in blue, then what we obtain is that d mu dt is equal to mu p of t, which we can then separate 1 over mu d mu is equal to p of t dt, and thus natural log of mu is equal to the integral of p of t dt, or you can write that mu is equal to e raised to the power the integral of p of t dt. Okay, and then in general, we'll leave the constant out here because it eventually cancels anyway. So leave const out because it cancels, just as a note to be rigorous here. But this is what mu ends up looking like. And that might be familiar to you, but I thought it'd be nice to just kind of quickly derive that. Okay, so let's look at an example. So we have dy dt is equal to, plus y over 2 is equal to 1/2 e to the t over 3. Okay, so then in this case we can see that p is equal to 1/2, right? It's just a constant. And the integral of p of t dt is equal to t over 2 plus c. So that tells us that mu is equal to some constant. Again, the constant is going to cancel anyway, so it's not actually important, but let's just put it in there. So c e to the t over 2. Okay? And then we can just put this into our formula. So y is equal to 1 over c times e to the t over 2. Okay? Times the integral of mu times q, which in this case is the right-hand side, the 1/2 e to the t over 3. So doing a little bit of the algebra in one step here, you guys can verify this. If needed, we have 5t prime over 6 dt prime. Okay, so that's that integral of mu times q, and then mu of 0 times y of 0 on the right-hand side is just going to be contained in an integration constant. So then we can see here that the two integration constants from the definition of mu are canceling. And what we obtain in the end is e to the minus 3t over 6 times the quantity 6 over 10 times e to the 5t over 6 plus c. It's the integration constant. And we obtain for our final solution 3/5 e to the t over 3 plus c times e to the minus t over 2. Okay, so that's just doing our carrying out that integral. We get that nice solution in the end. All right, so that'll be those are the two solution methods for first order. We can also use things like variation of parameters, but for now, we're going to go ahead and move on to second order differential equations. So second order, and we'll look at linear ODEs first. So second order means that the highest derivative of the dependent variable that appears is second order. We can say that a general second order ODE can be written as d squared, or d2 dt squared, the second derivative of y, is equal to some function of t, y, and dy dt. Okay, very general there. The linear second order ODE can be written as d second derivative of y with respect to time is equal to g of t minus p of t dy dt minus q of ty. The minus signs here just so that you can you have all the dependent variables on one side of the equation being positive. It's really just a convention. It's not important. You can absorb those minus signs into those functions if you like. And then if g of t is equal to 0, then it's homogeneous. And we'll go ahead and start there. So start here with a second order linear homogeneous ODE. And to solve that, we use the characteristic equation. Which, by the way, is also due to Euler. Okay, so let's consider this general equation. We have a second order linear homogeneous differential equation with constant coefficients. So by that I mean we have a d 2y dy squared, or dt squared rather, plus b times dy dt plus c times y is equal to 0. And again, a, b, and c are constants. Okay, so let's replace the operator d by dt with r, okay? Excuse me. So if we did that, what we would have is we'd have a r squared plus b r plus c, this whole thing being an operator, acting on y is equal to 0. Okay, and so the only way that this can be true for any y is if a r squared plus b r plus c is equal to 0. And this thing is the characteristic equation. Okay? There's lots of things in mathematics that are called characteristic equations. You know, I think like the equation for the eigenvalues of a matrix is also often called the characteristic equation or characteristic polynomial. So that term is a little overloaded, but in this context, that's the definition. And then we find the roots of this equation. Find roots, which we'll call R1 and R2. Okay, and this is just done using the quadratic formula, or factoring the equation. Okay, and then you end up with the following, where you have R minus R1 times R minus R2 times Y is equal to 0. So this equation is satisfied if you have R minus R1 times Y is equal to 0, or R minus R2 times Y is equal to 0. So both of these scenarios would satisfy the overall equation. So then, if we solve this guy, what you end up with is to sort of reinsert the operator. You have d by dt minus r1 operating on y, or times y, is equal to 0. That's the same as dy dt is equal to r1y. We know that that's a separable equation. which gives rise to the following solution, r1 dt, which is then y is equal to some constant c1 times e to the r1t, right? And then we know that this equation is basically of the same form, so we're going to get a y2 here. I'm going to rename that y1 just because it's one component. Let's get the zoom right again. So y2 is equal to c2 e to the r2t. Okay, so the general, since either of these satisfy the equation, we need to be able to say that any linear combination of those two is what forms the general solution. So the general solution is just the sum of those two functions, c1 e to the r1t plus c2 e to the r2t, right? And then you find the constants using the initial conditions, right? Okay, so let's look at an example of this. So we have y double prime plus 4y prime plus 4y is equal to 0. The characteristic equation is r squared plus 4r plus 4 is equal to 0. And this yields, or this can be also written as r plus 2 squared is equal to 0. And so now we have a little bit of a solution of a problem, right? So, you know, we have only one value for r. So we have repeated roots. Okay, so we know one solution is going to be one solution will be y1 is equal to c1 e to the minus 2t. Right? But we need an additional linearly independent solution since it's the second order equation. So for second linearly independent solution, guess y2 is equal to some function nu of t times e to the minus 2t, right? And then we'll sub that into the original equation to find nu of t. So if we do this, we go through the following process where, you know, the first derivative is just nu prime of t times e to the minus 2t plus, or minus rather, minus 2 nu of t e to the minus 2t. That whole thing is going to get differentiated again, but just for this line, we'll only do it once. Nu prime of t, this is just 4 times the first derivative that we just calculated on the inside and the interior of the previous parentheses. E to the minus 2t, and then we have plus 4 nu t e to the minus 2t, that whole thing is equal to 0. So that's just the governing differential equation with everything subbed in. And we'll apply that derivative once again. So we have nu double prime of t e to the minus 2t minus 2 nu prime of t e to the minus 2t. And I'll just go ahead and proceed. You can sort of see how the pattern is going to shake out here, but I'll write out the whole thing. E to the minus 2t plus 4 nu of t e to the minus 2t. You know, as you can see, we're going to end up with everything having an e to the minus 2t in it, so then we can cancel that out. Nu t e to the minus 2t. In the end, plus 4 nu of t e to the minus 2t, the whole thing equal to 0. Okay, so first we'll cancel all these exponential factors because we can divide the whole thing by that since it's all equal to 0, of course. And then let's see how things cancel. We've got minus 4 new primes here and a plus 4 new primes there, so those are going to cancel that. We've got 8 positive news and then a negative 8 news here, so those all cancel. And what we end up with is just nu double prime of t is equal to 0. And we know how to solve this. This is going to give us a linear function for nu of t. So nu of t is equal to some constant t plus some other constant k, some other constant times t plus some other constant k. And that tells us that our general form for our second linearly independent solution is just our second constant, c2, plus, or times t times e to the minus 2t. Okay, so y is equal to c1 e to the minus 2t plus c2 times t times e to the minus 2t. And that's our general solution. Okay, and because the exponential coefficient is a double root of the characteristic equation, you're always going to get that nu of t is a linear function of t, so you can always use this form. Always usable for double roots. Okay? If the roots are complex, then you have complex exponentials and therefore oscillatory behavior. So like if R1, say, is equal to P to the plus IQ, that would mean that R2 is equal to P minus IQ. Since the roots are always going to be complex conjugates, then your solution looks like Y is equal to C1 times e to the px times sine of qx plus c2 times e to the px times cosine of qx. Okay, and that's just because e to the I theta is equal to cosine theta plus I sine theta. Okay? All right, so just keep that in mind for complex roots. So that's the characteristic equation. Now let's move on to the method of undetermined coefficients. So then this is for non-homogeneous second order ODEs. So method of undetermined coefficients. And this is actually very, very common, this one. Like I might say that this is, you might see this more during the quarter than a lot of the other methods that we'll talk about today. So, pay special attention to this one. Okay, this one also, just as a note, is also due to Euler. So this is Euler. This time, he did this in 1748. And he actually found it when he was analyzing perturbations to Saturn's orbit by Jupiter. And I think it was for to win us the annual mathematics prize in Paris. I think he won it for the first time. I don't know if this is the first time he won it, but he won it for the first time when he was 20 years old, and then he went on to win it like another 17 times in his life or something on that order. But I found the initial publication you can see here. So, basically, this is French, of course, but you can see it's talking about these inequalities, these perturbations to Jupiter's orbit due to Saturn's presence, and then you can see here method of this is where he's talking about the method of undetermined coefficients right here, and he proceeds to lay out the method that had never been used before to solve that problem. So he just casually worked out a new solution method to solve that problem. Okay, so let's go ahead and hop into it. So we still have a second order ODE that's linear with constant coefficients. So it's like y double prime minus 3y prime minus 4y. But we have some sort of forcing function, so it's non-homogeneous. We have 3 e to the 2t. So the homogeneous part of the equation we just use the characteristic equation to find that. So, we know that this is going to be, r minus 4 and r plus 1 is equal to 0. So our two roots are r equals 4 and minus 1. Okay, so then the homogeneous part yh is equal to c1 e to the 4t plus c2 e to the minus t. Okay, so that's the homogeneous part of the solution. And then we make a guess or an ansatz. We make an ansatz. This word just means intelligent guess. Ansatz for the particular solution. Where we guess that the particular solution is going to be of the form some constant times e to the 2t. Okay, and in other words, we're guessing that the particular solution is going to match the forcing function in form. And if we sub that into our differential equation, then we get 4a e to the 2t minus 6a e to the 2t minus 4a e to the 2t is equal to 3 e to the 2t. Okay, so all the exponential terms cancel, and we can see that a is going to end up being negative 1/2. Okay, and then in the end, y of t is equal to the sum of the homogeneous and the particular parts, and so you get c1 e to the 4t plus c2 e to the minus t plus minus 1/2 e to the 2t. Okay, and that's our final solution. Pretty straightforward. Now, one thing to note is that the particular solution needs to be linearly independent to each term in the homogeneous solution. Okay, so yp needs to be linearly independent of yh. Okay, so like if we had say y double prime minus 3y prime minus 4y is equal to 3 times e to the minus t. So in other words, the forcing function is the same form as one of the components of our homogeneous solution. Then we need to adjust our ansatz. Then adjust ansatz to yp is equal to a t e to the minus t. Okay? So keep that in mind. Just multiply by a linear function. So there's a few types of forcing functions that you need to keep in mind. This will be a useful table for you to keep for later use. So consider the equation y double prime plus a y prime plus b is equal to f of x. F of x. Okay, if f of x is, that's going to be one column of a table, and then the next column of the table will be then yp is. Okay, so this is like a decision tree for which functions to use. So if the function is exponential, e to the px, then yp is going to also be exponential, the same form, unless, of course, that it's not linearly independent of the solution, so keep that in mind. If it's a polynomial of order n, so if it's like k x to the n, then your yp is going to be a polynomial of the same order, but you have to include every term of smaller order in the polynomial, okay, all the way down to k naught, the constant term, okay. So that's what you need to do for polynomials. And then if it is either, if it's a trigonometric function of either type, then you need to have your yp be the sum of both. It needs to be k cosine of qx plus m sine of qx, okay, for every frequency that appears, a frequency being that constant q that appears in f of x. Okay, both are important. So they can't be a linear combination of the homogeneous solution components. And so, you know, if yp is a linear com of homogeneous solution, components, then multiply by x or x squared, and the x squared case comes from repeated roots in the homogeneous equation, because in that case you would already have x times that function. Okay, and let's go ahead and look at an example of this. So if we have y double prime minus 2y prime plus y is equal to e to the x plus x, and we look for, you know, yh, then we're going to have r squared minus 2r plus 1 equals 0. This is going to lead to a repeated root, r minus 1 squared equals 0. So therefore, the homogeneous equation solution is equal to c1 e to the x plus c2 times x e to the x. Okay, and then our particular solution, yp, is going to have the component that's due to the polynomial presence, so that's going to be k1x plus k naught plus c times x squared e to the x. Okay, so that's keeping in mind this rule that I said here. We had repeated roots in the homogeneous equation, and the e to the x is not linearly independent of our particular solution. Okay, so we're going to go ahead and sub that in. which I am not going to do here. I'll let you work that out. It's just algebra in the end of the day. But what you'll end up with is that C is equal to 1/2, K1 is equal to 1, or here, I'll go to the last line here because it shows you how you solve this in general. So once you sub this into the equation and cancel all of the like terms, what you end up with is an equation that's like this. It'll be 2c e to the x plus k1 times x plus these two constants added together, k0 minus 2k1 is equal to, on the right-hand side, e to the x plus x. So this left-hand side just comes from plugging in yp into the left-hand side of the equation and crunching numbers, evaluating derivatives and crunching numbers. But what this tells you is you can sort of compare across terms. So you know that 2c is equal to 1, because that's what's in front of the exponential term. You know that k1 is equal to 1, and then you know that k0 minus 2k1 is equal to 0, which then, of course, lets you know that k0 is equal to 2. Subbing in 1 for k1. Okay, and so then the final solution becomes y of x is equal to yh plus yp, which is c1 e to the x plus c2 x e to the x plus 1/2 x squared e to the x plus x plus 2. And that is your solution in this case. Okay? We have one more method to cover, and then we'll be done for the day. So the last method is called variation of parameters. Okay, and this method is due to Euler as well, but it's actually mostly due the one who really formalized it the best. So Euler did touch on this first, but the person who really put it together in the method that in the way that we use it today is Lagrange. Okay, and I think I have an image of Lagrange here. Yeah, there you go. So that's Lagrange there, and also the publication, the original publication of variation of parameters. You can see that it's in French, of course. And Lagrange he's kind of like he's extremely important as well. He was the one who really came along and elucidated the mathematical structure of Newton's laws. So, he systematized the formalism behind those laws, and he also finally systematized the principle that underlies essentially all of physics, which is the principle of least action. If you ever take an upper division physics class of mechanics, like classical mechanics, you'll learn about Lagrange's equation and that whole mathematical formalism, and it's very beautiful. It's a very nice way of recovering physical laws from a very simple principle, like the principle of least action. I think Lagrange, yeah. So he's sort of considered one of or Euler's student, right? It was an informal relationship. It wasn't like a PhD student relationship, but he was one of Euler's students, frequent collaborators. So they were closely linked, and that's why this method can be attributed to both of them. Okay, so let's talk about variation parameters. So if our forcing function is not of a form that is amenable to the method of undetermined coefficients, then we need to use variation of parameters. So use when forcing function is not usable, or forcing function makes undetermined coefficients impossible. Because this is harder, this method is more work to solve. And there's some problems where this is less work than undetermined coefficients. But most of the time, variation of parameters is more complicated and easier to make a mistake. So you want to use it very undetermined coefficients when you can. Okay. So in this case, what we have is y double prime plus f of some function f of x of y prime plus g of x of y is equal to r of x. Okay. And let's say we already know what yh is. We know that we know that yh is equal to c1 y1 of x time plus c2 y2 of x. Okay, so we've already determined the homogeneous equation. For the particular solution, we're going to make a guess. For yp, make ansatz of the following form, where yp is equal to u of x times y1 of x plus v of x times y2 of x. Okay? And then to determine u of v, we need two equations. One equation results just from the original ODE, plugging it in, and the other is free for us to choose, actually. So we do so in a manner that simplifies the analysis. So there's two equations. Need two equations. So one of them comes from the ODE, which tells us that u prime y1 prime plus v prime y2 prime is equal to r of x. Okay, that just comes from plugging this into yp into the differential equation. You can do that on your own if you like. And then we make one clever choice because it's free. And the clever choice of equation is u prime y1 plus v prime y2 is equal to 0. Okay, and we make that choice so that when we sub it into the ODE, there are no second order derivatives of u or v. Okay, so this choice actually leads to this simple form of when we actually plug it into the ODE. All right, so leads to no second order derivatives. Okay, so that's what makes that choice clever. And we can solve this system for u prime and v prime and integrate. So like algebraically. So this is like an algebraic system for u prime and v prime, and then we solve it and integrate. So solve plus integrate. And you get the following, which is that u is equal to minus the integral of y2 times r over w, and I'll say what w is in just a moment, times dx. And v is equal to the integral of y1 times r over w times dx, where w is called the Wronskian, which is the determinant of the matrix y1, y2, and y1 prime, y2 prime. So that's y1 times y2 prime minus y2 times y1 prime is the Wronskian. Okay? So then yp becomes minus y1 times the integral of y2r over w dx plus y2 times the integral y1r over w dx. Okay? And you know, sometimes the Wronskian ends up being a really simple function, and it plays well with y1 and y2, like when you have a lot of exponentials involved. So this method can be very simple, but most of the time you should go with with the characteristic equation first. Okay, so let's go ahead and summarize all of this. And then we'll be done. So in summary, what method should you use when? Well, if you have first order ODE, our methods that we talked about were separation of variables, crucially, this is actually applicable to equations that are both linear and nonlinear. So that's something to keep in mind. Should always be looking, really, this is the first line of defense, I would say. It's like you should always look and see if the equation is separable if you have a first order ODE. Or even a second order ODE. You can apply separation of variables twice in a row to integrate things. That's what we did when we saw that nu double prime of t was equal to 0. That was just separation of variables twice, essentially. Okay, we talked about the integrating factor. This is basically just convert non-separable to separable. I didn't say that before, but that's essentially what you're doing there. Okay, so you're just moving up to separation of variables. We also can use variation of parameters. We didn't talk about using this for first order ODEs, but there are notes in the that are available through Canvas that you can go and look through these. It won't come up in the class very often, if at all. So you don't have to worry about it too much. So variation of parameters, that's where you have a single homogeneous solution. So it's just the same as what we just covered, basically, but you just have a single homogeneous solution. So that's why I only covered the second order version. And then there's where we really didn't cover this, which is a method called order reduction. Okay, so this is where, given one solution of second order equation, let's call it y1, assume y2 is equal to v of t times y1 to reduce the equation to a first order equation for vt, to reduce equation order. That's the entire method in a nutshell. Okay, even though we didn't cover it, that's really all you do. You just make that assumption and plug it in, and then you'll end up with a first order equation left over that you should know how to solve, or that you likely will know how to solve. So for second order, that's not how you spell order. Second order ODEs, let's also leave a letter out there. We have homogeneous constant coefficient equations. So homogeneous constant coefficients. That's going to lead us to the characteristic equation. When we have variable coefficients, I should say homogeneous variable coefficients, homogeneous variable coefficients. So that's where the coefficients depend on where the coefficients depend on x, say, or t. Okay. What you do there is you convert it to a constant coefficient. Convert to constant coefficient by assuming y is equal to x to the m, raised to some power m. Okay, so that's another thing that didn't get explicitly covered in this lecture. You should still know how to do it. It's less common. I can't remember if you'll see it on your homework, but if you do, again, that's something that shows up in the course notes that are posted on Canvas. Okay, and then we have non-homogeneous equations on the second order front, and that's where you use method of undetermined coefficients first, and if that one doesn't work, we'll use variation of parameters. Okay, so that's the end of today's lecture. Hopefully it's not too dry. It's a lot of review material, but I'm hoping that if as you went through it, you actually felt like, oh, I remember that, and it just served as a way of jogging your memory. And then when you encounter all of these solution methods in the homework, you'll be ready to go. So the next lecture, we're actually going to start by going over these definitions again. I probably should restructure and do these at the end, but these sort of definitions like homogeneous and linear versus nonlinear, we'll go ahead and go through those and define those rigorously. Second order, first order, stuff like that. And then we're going to actually go over a bunch of modeling examples and show you where these different types of equations can pop up for different physical systems. Okay, so another purely paper and pencil lecture, and then the following lecture after that we'll actually start to get into some numerical methods. Okay, so thanks for listening. I'll see you in the next lecture, and you have a great remainder of your day.